Alright, welcome back. In this video, we're going to go over the intro to alkanes and parent chains, as well as I'm going to mention why HIV and AIDS is so difficult to cure, and introduce techniques that researchers are using in modern day medicine to actually cure it. So what is an alkane? First off, it's basically a molecule of single bonded carbons and hydrogens lacking other functional groups. It's basically the most boring, typical molecule you'll see in organic chemistry. Here are some examples. Here we have propane, butane, and pentane. Notice that they all end in the suffix ane, as in A-N-E. That's how we know it's an alkane. Propane has 3 carbons to it. Let's draw it up. 1, 2, and 3. Butane has 4. 1, 2, 3, 4. And pentane has 5. 1, 2, 3, 4, 5. And to those carbon atoms, they have hydrogens attached to them. Single bonds are flexible. So therefore, alkanes tend to be flexible. But why are alkanes important? Why do we need to learn this? Okay, so the HIV/AIDS virus is obviously a very terrible, awful virus. But the reason it's so difficult to actually cure is because it can mutate. HIV virus has the ability to change its shape so drugs are less effective against it. So you give a medicine or drug to a patient with HIV. What HIV is going to do, it's going to mutate and change its shape so the drug will no longer work on it. And this is why it's so difficult to cure. So here's what researchers are doing. So this is a picture of a researcher. This is actually my best friend, Cavelli. She's at Cal Poly SLO right now. Super, super proud of her. She's doing amazing work in research. Really proud of her. Anyhow, what researchers are doing is they're trying to make drugs now that are flexible. Because if you make the drugs flexible, it can mutate or change its shape with the virus, so the virus cannot adapt. And this is the way that we're basically in modern medicine trying to combat HIV. And this is what direction we're trying to take to cure it. Because if you can make the drug change shape along with the virus, then that should work, in theory. But how do we make these drugs flexible? Well, like I said, alkanes are flexible. So let's put some alkanes into these drugs to make it flexible so when the virus mutates, the drug can follow. And it can actually kill the virus. This is why it's important. We're learning this. So let's talk about naming alkanes. We name the alkane based on the number of carbon atoms that we see. For example, if the molecule has 1 carbon atom, we call it meth. The parent is called meth. And what we do is we stick the suffix ane after it. So it comes the parent, then we put ane after it. So it's methane. For example, butane has 4 carbon atoms. Bute, or we say it's actually but or bute, and we add ane at the end. Butane. For example, 7. If the molecule has 7 carbon atoms, we call it hept. That's the parent. And we just add ane after it. Heptane. Let's look at the previous slide, actually, the first one. Propane has 3 carbon atoms. 1, 2, 3. Okay? So you go in the chart. 3 carbon atoms means it's prop or prop. And we just add ane at the end, and we got propane. Ta-da! Same with butane, same with pentane. Now, once if you have a complicated molecule like this, not the simple ones from earlier, the first thing you need to do is you need to identify the longest carbon chain in the molecule. And this is what we call the parent chain. Here we have a complicated looking molecule here. So what we have to do is you have to find from this entire molecule, if you were to stretch it out, what would be the longest carbon chain? So here's what we do. We start numbering them from left to right. So we're trying to find what the longest combination would be. So this 6, 7, 8, 9. This would be the longest chain. Here's what we cannot do. Here's what we cannot do. We can't call this 1, then go 2, then go 3, and call this one 4, and then go here and call this 5. You cannot go back down. It has to be in a row. So for example, we can't do this. 1, 2, 3, 4, 5, 6, 7, 8. We can't do that. We can't go backwards. We have to go all in one, basically one in a straight linear fashion. 1, 2, 3, 4, 5, 6, 7, 8, 9. We do not go backwards at all. And this is the longest chain of 9 carbon atoms. So since it's 9, it's nonane. This is actually not called nonane because there are stuff that's branching out of this. Do you see these other ones that we did not count? That's not part of the parent chain. This actually is involved in naming the molecule, but we're going to get that into the next video. But just know what the parent chain is. Now, what happens if you have a molecule with multiple of the same carbon length chains? Here we have 2 examples here. Same molecule, but both computations that I wrote out here in red, the ones that are like the red here, both are 7 carbon atoms long. So what do we do? What's the longest? What's the correct one? Well, I already told you what the correct one is. It's on the one on the left, but the reason it's correct is the number of branches that come from the carbon chain will indicate which one is correct and which one's incorrect. More branches, the better. Here on the left molecule, coming from the carbon chain, we have 1 branch, 2 branches, and 3 branches. Compared to this one, it has 1 branch and 2 branches. You may be thinking, wait a second, isn't this a branch right here? You would be right. However, it's not coming from the parent chain directly. It needs to be actually physically attached to this long chain here. So it's branching from here. There's only 1 branch there and another one here. So it's only 2. We group this 1, 2. Compared to this one, we have 1, 2, and 3. Like that. 3 branches coming off of the carbon chain itself, not like branches from away from the carbon chain. So that's why the one on the left is correct. More branches, the better. So let's do some practice problems. Identify the parent and name it. So you have this complicated molecule here. What is the correct answer? Is it the one on the left or the one on the right? Well, let's figure it out. Let's count the number of branches. The one on the left has 1 branch, 2 branches, 3 branches, and 4 branches. Compared to the one on the right, we have 1 branch and 2 branches. This whole thing is 1 branch, even though it looks like it's branching off here. But how many are coming off from the parent chain itself? Just 1 here and 2 here. So the one on the left is correct. This one's correct. Hey, what about B? What is the parent chain? Oh, sorry, we have to name it. Almost forgot. All right, this is how we name it. We're not going to name the substituents yet. We're just going to name the parent chain. So you have 1, we have 2, we have 3, we have 4, we have 5, 6, 7, 8, 9, 10 carbon atoms. So let's look at the chart. 10 carbon atoms means it's a decane molecule. like that. Okay, what about this one? What is the longest chain? Now you'll probably be quick to think, okay, wait a second, I think I know it. It'd be this 1, 2, 3, 4, 5, 6, 7. Because it looks like it's longest. But you would be mistaken actually, because it is actually 4, 5, 6, 7. This is the correct answer. And why? It's about the branches. This molecule with this configuration here has 1 branch, 2 branches, and 3 branches. Unlike if we do this, if we call this 6 and 7, it would have only 1 branch and 2 branches. So that's why this configuration is correct. It would be this 5, 6, 7. Okay, you have 7. So this is heptane, because 7 means hept. Like that. Okay, what about this one? This is a trick one. This is a trick one. Okay, you would probably be thinking it would be 1, 2, 3, 4, 5, 6, 7, and 8. This is not right. Because it branches off of here. Okay? We cannot go this way and branch this way. That's not allowed. And this is special circumstance, because this is called a cyclo. Actually, I don't want to name the number of carbons yet. But this is a cyclic molecule. It's a circle. So we cannot actually branch off like this and call it like that. It terminates here. And we call this one branch. So the correct answer is this. And yes, now let's count the carbon atoms. 1, 2, 3, 4, 5, 6, 7. It's a 7. So this is a heptane, a cycloheptane actually. Cycloheptane, so cycloheptane. Like that. Because it's in a cyclic form. It's basically a round circle. Not a circle, but it's in a circular looking format. And that's why we add the word cyclo in front of it. Instead of being just a heptane, we say cycloheptane to indicate it's circular. And that's basically it for the intro. I'm going to get into more of naming it in the next video. But if you found this video helpful, please like and subscribe. And until next time, later.